Good morning, ladies and gentlemen, and welcome to my presentation about processing of flexible glass in sheet-to-sheet processes as part of the session New Printing Approaches 1. I'm afraid I have to disappoint you right at the beginning of my presentation, as I will not present a new printing approach, but maybe a new thinking approach. So let's see what you can take away from my presentation. Let me briefly introduce myself. My name is Wiebke Langgemach. I'm a PhD student at the Fraunhofer Institute for Organic Electronics, Electron Beam and Plasma Technology, FEP, which is located in Dresden in Germany. I'm part of a research group dealing with thin film coating using sputter technology, but my own specialties are glass technology and glass-related questions and issues. I would like to take the opportunity today to talk to you about flexible glass processing. As you all know, printed electronics are omnipresent today. Just think of RFID, photovoltaics, lighting applications, and last but not least, displays. Especially wearables and foldable devices will gain importance in the coming decade. And as you can see in the diagram, exponential growth is predicted for the foldable display market. And as you might have noticed, first smartphones using foldable glass displays are already on the market. So what are the advantages of flexible glass? Of course, obviously it's lightweight compared to normal thick glass. Moreover, it's stable and resilient, shows low surface roughness and no oxygen and water permeability at all. As you can see, it has some important advantages compared to polymer webs. Nevertheless, we have to face one important disadvantage. It's a brittle material, so processing and handling are difficult. My objective today is to give you an insight into our research facilities and into current research results. To do that, I will start with presenting our research labs. Afterwards, I will present the current project results of different projects. And in the end, I will give you an insight into our latest efforts concerning the mechanical characterization of substrates and thin films. I'd like to give you some background information at first. Research at FEP about flexible glass started in 2013, and we have cooperations with all relevant glass suppliers in that field. As you can see in the table, we can offer sheet-to-sheet processing as well as roll-to-roll processing, and we are able to deposit inorganic thin films as well as OLEDs. My research group deals with sheet-to-sheet processing. We are using the vertical inline coating tool you can see in the picture. We have a smaller machine as well with a similar setup. Both machines were originally designed for rigid substrates, but we are able to process flexible substrates as well. Normally, we handle glass with thicknesses of 100 micrometer, but 50 micrometer are possible as well. We can offer pilot scale coatings using different sputtering technologies and different pre- and post-annealing steps. So much for our research facilities. Let's now turn to our current projects. At the moment, we are working on a large research project called Glass for Flex. It's funded by the German Federal Ministry for Education and Research, and the overall intention of the project is to develop new process technologies for flexible glass applications in optical systems. As you all know, optical systems have very high demands concerning the thin film quality and the resulting film properties. Therefore, developments for using flexible glass in that area seem necessary. The project covers the whole value chain, beginning with the production or manufacturing of thin glass. The Schott company is our project partner who develops that. Afterwards, when beginning the processing in our house, a cleaning step is following, and our partner Schmid develops a washing machine for flexible glass. Cleaning is a crucial step in the process chain. Afterwards, an inspection step follows, where you can sort out substrates below the required quality standard before the cost-intensive coating. That leads to higher yields in the coating process itself and cost reductions, of course. Our partner GBS is developing a system to do that. Of course, handling and transfer are crucial as well because the substrates may neither be polluted nor damaged during these steps. We have two partners, Adenso and Project Carrier Systems, who develop new systems to do that. Last but not least, FEP is responsible for the flexible glass coating. That includes PVD processing as well as surface refinement. As I already said in the beginning, we only use flexible glass in sheet-to-sheet processes here. The sub-project of the FEP covers mainly 3 topics. First of all, the deposition of PECVD layers as adaptation layers between the flexible glass and PVD coatings. Then we want to deposit zirconium dioxide as a basis for scratch protection systems. And we are depositing indium tin oxide as a transparent electrode and use different thermal annealing steps. The overall goal of this sub-project is to optimize the electrical and optical properties as well as the thin film stress of the films. Concerning the electrical and optical properties, at FEP we have scientists that are experts for years. Thin film stress was already important before, but we focused on adhesion tests and environmental durability. Now, with the usage of flexible substrates, bending and curvature gain importance. They are new aspects of this theme. Let's now move on to some selected project results. Let me go back to what I said about adaptation layers and have a closer look at the results. First, I want to give you a very short explanation what the PECVD process is like. PECVD means plasma enhanced chemical vapor deposition, and this is a process where an organic precursor is deposited on a substrate. We used HMDSO, which is hexamethyl disiloxane, but that needed to be evaporated at first. The process gas is then transferred into the processing chamber through specially designed inlets. Another gas, the so-called reactive gas, is intruded too. In that case, we used oxygen. Both gases are mixed, and the mixture gets in contact with the plasma. The plasma electrons and also plasma atoms collide with the gases and cause different kinds of reactions, for example, dissociation. Afterwards, the mixture or the organic precursor is deposited on the substrate. As a result, you get a partly inorganic thin film. As you can see in the table on the left side of the slide, the organic thin film shows quite similar characteristics compared to normal sputtered silicon dioxide, except for the deposition rate and the thin film stress. As you can see, the deposition rate was doubled in this setup. Of course, it strongly depended on the process parameters. And the thin film was significantly lowered. The original idea was to use these low-stress films in anti-reflective layer stacks in order to decrease the overall film stress. On the upper left side on this slide, you can see an illustration of such a system. You can see that you use alternating layers of high refractive and low refractive materials in order to decrease the overall reflection of the substrate surface. In this project, we used 6 single layers with different thicknesses that you can read in the middle of the slide. Only one side of the substrate was coated. We used silicon dioxide as a low refractive and zirconium dioxide as a high refractive material. We used PECVD deposited silicon dioxide as well as sputter deposited silicon dioxide in order to show the differences in film stress. In the picture on the right side of this slide, you can see how we normally fix our samples to the vertical carrier system. Let's have a closer look at the results. Please have a look at the diagram at the left side at first. There you can see the reflectance after the coating, and you can see that both anti-reflective systems are very effective. We've lowered the overall reflectance by 2 up to 4%. Please keep in mind that the backside of the substrate has a reflectance of approximately 4%. Both systems are effective, but of course they are not optimized because, as I said in the beginning, we focused on the thin film stress here, not on the optical properties. The table on the right side shows that we clearly reached our goal to produce anti-reflectance systems with lower film stress. We were able to reduce the overall film stress by 25% by the usage of PECVD deposited silicon dioxide instead of sputtered silicon dioxide. I'd like to expand on the aspect of thin film stress, showing another example. In this slide, you can see the results of our experiments using 150 nanometer of indium tin oxide coating on 100 micrometer flexible glass. Please have a look at the left side at first. There you can see the dependency of the thin film stress on the process parameter oxygen flow during the sputtering process. The negative sign indicates compressive stress here. You can see that you get a higher absolute film stress with increasing oxygen flow in the process. One can assume a slightly decreased stress after the annealing process. If you now use this data to get a linear regression and then combine them with the resistivity values, you can generate the diagram you see on the right side of this slide. You can see the dependency of film stress and the resistivity. It shows that the resistivity is clearly decreased by annealing processes and that also the annealing might slightly decrease the film stress. Please keep in mind that the upper left side of, or upper left corner of this diagram is the desired area of properties, because thin films with low film stress and low resistivity are desired for many applications. That's all I have to say about our project results in the Glass for Flex project. Let's now have a quick look at another project. Starting in April, we will work on a project called Custom. It is focusing on flexible glass as well, on mechanical characterization, especially edge strength and fatigue behavior. It's a joint project with the IMVS in Halle. Companies can join in the advisory committee to get insight into project results and access to the results. As I said, fatigue testing is an important part of the Custom project, and that's why I want to give you an insight into our latest efforts in that area in this last part of my presentation. Yuasa System, our partner from Japan, developed tension-free testing methods for flexible substrates. The problem with normal testing methods using, for example, rods, is that there are large tensile stresses occurring in the sample. You can see an illustration of such a test setup in the upper right corner on the slide. In the bottom part of the slide, you can see the illustrations of the both testing methods available at FEP. Both are tension-free, and they are suitable for substrate as well as device testing, not only flexible glass, but all other materials as well. The clamshell type is especially suitable for small samples and small bending radii. And you can see an illustration of the jig movement in the lower right corner on the slide. We are currently developing an inline measurement method for the electrical resistance, and thanks to our partner Yuasa, we will soon be able to detect the bending mechanism by the use of the camera. The U-shaped folding test is also suitable for bigger substrates as well. You can see an illustration of the jig movement on this slide too. We developed a possibility to carry out two-point bending experiments using the same test setup. At last, I want to give you an example of bending tests we are currently doing at Fraunhofer FEP. We produced samples with a similar design like for the film stress experiments and bent them until breakage. As you can see in the diagram, no significant influence of the deposition process can be detected. In former experiments, we found out that the surface strength is significantly lowered by the deposition process, but coating might reduce the influence of edge flaws, and therefore no influence can be detected in total. You can see there's a significantly lower fracture angle after the annealing, because the annealing step generates defects, and that confirms results from previous experiments. The next step will be to analyze the fatigue behavior of flexible glass. Let me now conclude my presentation. I hope I've shown you that flexible glass is a material worth a thought or even try. And I've made clear that it has some important advantages compared to polymer webs. I've shown that we've made some basic investigations concerning the stress and fatigue behavior of flexible glass and demonstrated the expertise of Fraunhofer FEP in sputter coating. So I want to thank you for your attention, and I'm happy to answer your questions afterwards.